Understanding these 5 examples is crucial to your understanding the concepts in mass moment of inertia. Now you may notice that only in the first example, I calculate the mass moment of inertia at the center of gravity, which is point O. And also I choose another arbitrary point to find the mass moment of inertia for this cylinder bar. As we expected that the mass moment of inertia at the center of gravity is lower than the value of mass moment of inertia calculated somewhere else. For all other 4 examples, you may notice that I did not choose the center of gravity for finding the mass moment of inertia with respect to the x-axis as well as with respect to the y-axis. I will leave those to your exercise after the class. So how do you do that? First of all, you can use the integral approach by finding the center of gravity. In this case, it's very simple. It's at the center of geometry, which is 1/2 of b from the y-axis and 1/2 of h from the x-axis, which is in the middle of this rectangular plate. You plug this in, and you change this integral from 0 to h to from negative h over 2 to positive h over 2, and you will see that the result is going to be different. And we all expect that this result must be lower than the values we have found here. Another approach you can use in finding the mass moment of inertia at the center of gravity is by using the parallel axis theorem. Because whatever we calculate for the other 4 examples in this expression is not the value right here, is not Ig. What we found for the 4 examples is this value, I here. Therefore, you can use I equals Ig plus md squared to find Ig. How do we do that? In this case, this Ix is 1/3 of m times h squared. We know that this is not Ig, this is Ix. So you can relate this Ix to the Ixg plus md squared. In this case, what is the value of d? And that is the distance from the center of gravity to x-axis, which is from this point to x, and that distance is simply h over 2. Therefore, in order to find Ig, by using parallel axis theorem, you can just write down 1/3 of m times h squared equals Ix or Igx plus md squared. And d is replaced by h over 2. And by doing that, you can find Igx easily. Similarly, you can also use the same parallel axis theory to find out the Igy by relating 1/3 of mb squared equal to Igy plus md squared. But just keep in mind that in this case, the distance d is not h over 2, but it's the distance from the center of gravity to the y-axis, which is b over 2. The same approach can be applied for finding the mass moment of inertia at the center of gravity for this triangular plate, as well as this triangular plate. Besides the 2 approaches I demonstrated in this class to you in finding the values of mass moment of inertia with respect to a chosen axis, the 3rd approach is what we call radius of gyration. If you are provided with a value of radius of gyration, and the mass moment of inertia can be determined by simply the product of total mass times the radius of gyration squared. However, because the value of mass moment of inertia must be specified with respect to a chosen axis, the value of radius of gyration must be provided again with respect to a chosen axis. Therefore, if you are provided with different values of radius of gyration with respect to different axes, you have to pay attention to the right axis to use. If you are provided with kx and ky, you have to know that by using kx, you are finding ix. If you are provided with ky, it is the value of iy that you are finding. Mathematically, certainly we know that radius of gyration denoted by regular k equals the square root of mass moment of inertia divided by total mass. Now, there are many other ways we can also use to find the mass moment of inertia. And one more thing you want to remember before we finish today's lecture is to determine the center of gravity. And to do that, you will have to use the first moment of area, which is shown here. This is the x bar and y bar expressions you can use in finding the center of gravity. So let's summarize what we have learned today. We start by introducing the definition of mass moment of inertia, which equals to the second moment of volume times the constant mass density. If mass density is not constant, and then this integral will have to be divided into the summation of several integrals, depending on the value of mass density. And after introducing the mass moment of inertia definition, we know that mass moment of inertia must be calculated with respect to a selected axis. That means for a three-dimensional object, you may have three different values of mass moment of inertia with respect to three different axes. The only case that objects will carry or have the same values of mass moment of inertia on both the xyz axis will be the case of spheres. We also talk about the parallel axis theory, and then we start solving these 5 different examples. I encourage you to study these examples, follow the math carefully, understand that where do we make the conversion, how do we determine the linear equation, and how do we carry out these integrals. These are simple mathematics which I believe that you can practice at home. After that, we also talk about the definition of radius of gyration. And in the next lecture, I will show you there are other properties from mass moment of inertia that we can utilize in determining the mass moment of inertia of complicated objects. Now, if you have questions about today's lecture, please remember to post your questions on the Blackboard system or send me an email via the SIS system. I'll see you next time.